Okay, hopefully this video will continue. Where am I? Okay. So there's this way of doing an electron configuration. There's these other weird ways. Just for those watching the video, this is table 6.3. Two other ways to do electron configuration, and there's the condensed electron configuration. There's another way of denoting these. So now I'm going to show you another way we teach. But this next way is what we call the 4 quantum numbers. So the equations you would use in a quantum mechanics description, we'll do a very low-level approach of quantum mechanics. That's the chapters before this. In this chapter, the sections before this section. I think this textbook does it exactly backwards. I would start with what they do at the end of the chapter and go towards the other stuff. But picture huge, excruciating equations, and you can use these equations to solve for, say, how much energy there is in this electron right here. The big ugly equations you would use would take 4 parameters that you would just plug into the equation and would give you the energy. There's another quantum mechanics equation that you could use to, say, map out, like here's the nucleus, and I want to map out where this electron travels. And let's say it travels like this. It would map out that, what we call the orbital. The orbital actually looks kind of weird like that. It's not just a line on a flat surface. So you'd use that other equation, you plug in the 4 quantum numbers for that electron, and then you could plot that. So just telling you what the quantum numbers are, why they matter, why there's this now a whole different way to express an electron configuration. It's because those are parameters in quantum mechanical calculations. So, you already understand some of these numbers if you followed what I told you. I'll put the S over here. Those are S orbitals. They're spherical. And if I go back over these S's and I just number them, 1, 2, it's 2S, 3S, 4S, 5S. That number, the 1, 2, 3, and 4, that's the first quantum number. That's called N, lowercase n, known as the principal quantum number. All right, so for any one of these, you've got your number 1 level, your number 2 level, your number 3 level, but yeah, it's split up into this, but this and this, or I'll go with the 3 level. And you would call these the, I'll say orbitals, the number 3, suborbital, suborbital, suborbital. But this is 3S, this was 3P, and this was 3D, so 3, 3, 3. So any electron in here that I've got circled have the quantum number 3 for N. All right, the next one, L, the angular momentum quantum number. That one relates to whether it's in the S, the P, or the D, or even the F. But when you use numbers there, the single ones, the S's, we give them a 0 here. The P's have a 1. The D's have a 2. And when you get to the F orbitals, they're 3. Let me write this. If you followed what S, P, D, and F are, It's literally just a translation to these numbers. S means 0, P means 1, D means 2, F means 3. There is a G and an H, which would be 4 and 5. And if you're cringing, the reason you're cringing is you're going, you just taught me that we represent these with these letters, and now you're telling me we're using these numbers. Yeah, this is actually another way to show an electron configuration. But using these numbers gives you the parameters for calculations you would do in quantum mechanics. So let's say we are in the number 3 level, and it's actually this electron that I'm trying to describe. This is kind of like an addressing system for an electron. Like you're sending a letter somewhere, and the first thing they do at the post office, they'll sort it into different states, and then they'll sort it into different zip codes, and then they'll sort it into different neighborhoods. Here's our first designation. We're in level number 3, so we're somewhere in here, and we're trying to specify this one electron right here. So that's 0, that's 1, that's 2, but we're in the one we represent with a 1. P is 1, so L is 1. If you're feeling confused, it's just because this is abstract. There's really nothing complicated about this. It just adds a layer of abstraction to it. So far we've said we're in the level 3, we're in the 3-1, so that's the 1, and now these, called the magnetic quantum number. When we have these, let me erase all this, just so it's not in the way, just so when you see this the first time it's obvious. This next addressing system, we hone it down a little closer. We do like this. I've specified we're in the number 3 level. I'm ignoring this. And then we specified we're in here in the p orbitals by putting a 1 here. Now we do this. We call this the 0, the 1, and that's the negative 1. All of these in the middle are 0. To the right, we put a 1. To the left, we put a negative 1. And up here, we put a 1 and a negative 1. And then out here, this is a 2 and a negative 2. And again, if it's bothering you, it's bothering you because it's abstract. It's not real complicated. You're looking at these numbers like, why the hell would you do this? These are the numbers you put into quantum mechanical equations to calculate things like energy and orbital shapes and a few other things. 1, negative 1, that'll be 0. So our third quantum number here is going to be negative 1 because we're trying to hone in on the purple one. So I'm going to say negative 1, 3, 1, negative 1. There's one more. This is called the spin quantum number. This is always going to be, and again, now you're going to go, now you're really screwing with me, Embry. This will be plus 1/2 or negative 1/2. Trust me, that's how quantum mechanics works. I can't give you a good reasoning why you would say this. But this one pointing up, we call the pointing up ones 1/2, and the ones that point down, negative 1/2. So this would be, and that's it. I know what a pain in the ass that is. It's just another way to represent electron configurations. But this one, the quantum numbers, is how physicists and quantum chemists calculate energies and complicated things about bonding and lots of other stuff we won't even come close to talking about. But the actual physics of how electrons move, and protons, I guess, but they're usually together in the nucleus, isn't classical physics, it's quantum physics, so you have to use quantum calculations. The beginning of a quantum calculation for a chemist is those four quantum numbers. All right. Let's leave silicon here. Was this silicon? I don't even know what I have up here anymore. 4S. 4S is full, oh, titanium. Well, let's just leave titanium here, and let me do one more of these abstract. Let's see, put that back. And let me pick another one. I'll make that one purple. All right. What are the quantum numbers for that purple one? Don't overthink it. What's the first? You got this, and then you got this, and you got these. This is the first shell, this is the second shell. So what is the N? 2. That's the second shell, so that's a 2. I'm specifying this. So look over here. These were the s orbitals. The 3s were the p orbitals. But in this new system, we use, the purple one is here. So instead of p, we're going to use 1. All right, the ML, that's the blue numbers. These. So this is 1. If you're sitting there confused, I swear you're overthinking it. And then that one's pointing up, so it's plus 1/2 or negative 1/2. So pointing up, we can, just by convention, we call that plus. If it's pointing down, it's negative. So if this little addressing system pinpoints this electron in a titanium atom. And if you wanted to know the energy in that, or orbital shape and some various other things, those are the numbers that you would plug into the big fat equation, and it would give you the answer you're looking for. Quantum mechanics is slick in that way, but it's not slick in the sense that those equations are extremely hard to solve. And they're not intuitive at all. So that covers a lot. I have, is that off again?
No, it's on.
It is on? Did I turn it off before? On. Okay, types of problems you might have, similar to those. 6, 7, 1. Oh, it turns out, based on this shape and these numbers we use for the quantum numbers, a couple of things that aren't obvious. There's the N and the L, and the M sub L, MS. For one thing, the number of orbitals in a N squared. This was the 1. This is 2. The 1, 3 is the 2 level. The 1, 3, 5. Cheat, make a little bridge up here. So level 1, level 2, and these are level 3. That goes with level 4. N equals 1. What am I thinking? Yeah. So 1 squared there's only one orbital. If n equals 2, then n squared is 2 squared, which is 4. 1, 2, 3, 4. If n equals 3, 3 squared equals 3 times 3 is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So handy if you're being asked very general questions, that maybe that's handy. But it just flows from the fact that this is the pattern. The pattern is in level 1, there's S. In level 2, there's S and P. In level 3, there's SPD. In level 4, there's SPDF. I didn't say this, but the insert at the bottom of every periodic table, that's where the F levels are filling up. But I'm not going to mess with you on those. Things just get more and more ugly above here. Things start overlapping. If you followed out the periodic table the way I was before, you'd see how ugly it gets. So there's that. One other thing to mention. L is from goes from n minus 1 down to 0. So when n equals 1, n minus 1, that is 1 minus 1 equals 0. 0 all the way down to 0, well that just means 0, that's that. Just 0. Watch how this works. N equals 2, and here, n minus 1 down to 0. So 2 minus 1 is 1, 1 down to 0. Oh, I forgot the, you have to do plus minus. I'll do that, plus minus. So now we've got 1 down to 0, down to negative 1. So 1, 0, negative 1. N equals 3. 3 minus 1 down to 0. So you got 2, 1, 0, and yeah, negative 1 and negative 2. For level 3, for the third one, when not n equals 3, yes. N equals 3, yes, when n equals 3, then L values, L equals this. So L equals 2, 1, 0. And negative 1 and negative 2. 2, 1, 0, negative 1, negative 2. So there's this isn't really a formula, but maybe you get what I'm saying. So handy little formulas if you're being asked very general questions. I think that's it for calculation tricks. So for n, there was n squared, that meant something. And for L, it's n minus 1 down to 0, with plus minus. Anyway, so for these first couple questions, that's useful. Leave that. I have written down 6.7172. I'll put these on a Word doc. 74, 75, 76, 77, and 78. But let's double check them and make sure they're not too ridiculous. So I would have been looking at 7.1. Okay. Without those extra weird little formulas I gave you, you could use those to answer this. Without using these, you can still answer this. What is the maximum number of electrons that can occupy these subshells? I was saying suborbital earlier. I meant subshells. The p orbitals, how many are there? How many orbitals are there with the p's? 1, 3, 5, 7, 3. And you can put 2 in each one, so you can have a total of 6. 1, 1, 3, 1, 5. So you can have a total of 6. There's a way to answer these types of questions like this. So for the 5D, for these questions, you don't really need this number. That's just kind of a distractor. You don't need the 5, the 2, the 4. It doesn't matter whether it's 2s or 3s or 4s. It's the same number of electrons that fit in an s. How many electrons fit in the s orbitals? What's that? 2. And you get 6 in a p orbital. How many you get in the d orbital? There's 5 here. You can fit 2 in each. So that gives you 10. You get 14 in the f orbitals. And by the way, if you look at the p block and you count from left to right, there's 6 slots. If you look at the s block, and you go from left to right, there's 2 slots. 2 rows. You see what I'm saying? That represents the 2 electrons. These 6 represent those 6 electrons. Across the transition metals, there's 10 slots there. And then the F ones, this insert down at the bottom, that's 14. As in 2, 6, 10, and then for the F, it's 14. So you can see that straight off the periodic table. What else do I have? All right. N equals 3 and then ML equals -2. Let's straighten this up. Because this is abstract, you can make yourself overthink it. Okay, it's not specifying everything here. So for this one, N equals 3 and ML equals -2. So 3 means we're here. I haven't drawn the 4s here, but there should be one more line there. All right. So we're in the 3 level. The 2 means 0, 1, 2. The 2 means we're in the d orbitals. So you can use that as a key for that. All right, and then it says a maximum number of electrons in an atom can have those 2 quantum numbers. All of these, I'll fill them in correctly. 1, 2, 3. All 10 of those electrons could start with 3, 2. If I fill this in, again, don't let the abstraction confuse you. This is just games with diagrams. You could have ML as 2. You could also have ML as 1, as 0, as -1, -2. And for these 2, you can have a +1/2, and the other one would be a -1/2. So each one of these electrons has a unique set of 4 quantum numbers. The first 2 will be the same, but you've got 1, 2, 3, 4, 5 different possibilities from here, and two more possibilities here. That's the 10 electrons there. So this question is saying maximum number of electrons that can have these 2 as their first 2 quantum numbers. It's those 10 in that d orbital. N equals 4, L equals 3. N equals 4. L equals 3. Guess I want to use this. So 3 minus 1 is 2, 1, 0, -1, -2. And we're in 3. L equals 3. Oh, this is supposed to be n minus 1. So n minus 1 is 3, so we go 3, 2, 1, 0, -1, -2, -3. L equals 3 is the f orbital. That's going to be the one that has 7. S has 1, P has 3, D has 5, and F has 7. So you could answer this by going, there's 2 electrons, 2, 2, 2, 2, 2, 2. So the answer here is going to be 14. But we could have figured that out this way. 1, 2, 3, 4, 5, 6, 7. There's 7 of those. That's these, literally these across here. And there's 2 for each. So there's 14 different electrons. They can start out with N equals 4, L equals 3. You follow that? All it is abstract. It's just games with diagramming and numbers. What else we got? I didn't write down uh, 6.73, but let me put an electron configuration here and show you. All right, what was this? So that's neon. Let's do at least sodium. Valence electrons are the electrons in the highest number n. So for this, what did I do? Sodium. For sodium, you've got the number 1 level, you got the number 2 level, you got your number 3 level. So the highest number here, the highest n we have here is 3. So the electrons in the 3 level are the valence electrons. And in this case, there's only 1. And everything else below it are the core electrons. But I don't tend to make vocabulary tests, so. One object is represented by the half arrows, that's the electrons. So yeah, I just didn't include this one. The direction of the electron indicates the spin. For each element, indicate the number of valence electrons, core electrons, and unpaired electrons. Core electrons and valence electrons, you could just get by looking at the periodic table. This is the same way we counted before doing ions. If you look at nitrogen and you count to the left and you point at nitrogen and you go 1, 2, 3, 4, 5. Those are 5 electrons in its valence shell. One row across is actually a valence shell. But just to sort of nail it home, nitrogen. Let's do nitrogen. So that and that. One, 2, 3, 4, 5, 6, 7. So nitrogen has 7. So I draw my 1, 1, 3, 1, 3, 5, and then I count up 1, 2, 3, 4, 5, 6, 7. That's the electron configuration of nitrogen. 1, 2, 3, 4, 5. These 5 in the number 2 level, those are the valence electrons. Point at nitrogen, 1, 2, 3, 4, 5. So you could draw this out, or you could just count across on the periodic table to get the valence. And everything else is going to be core electrons. What you can't get by just pointing, counting at the periodic table, pointing at the periodic table and counting, is how many unpaired electrons are there. If you did this correctly, you'd see immediately that there are 3 unpaired electrons. So this question asks, how many valence electrons, or here, nitrogen, number of valence electrons, number of core electrons, and number of unpaired electrons. Oh, and every one of these that I've been doing since I've been talking up here today, this is the ground state. We'll talk about what is the non-ground state, also known as an excited state later. I don't think we'll get there today. So these are all ground states that I've been drawing up here. So 3 unpaired electrons, 5 valence electrons, there's 2 in the core. Yep, 2 in the core. So you could make the diagram and then answer these questions. But the valence is easy to find by counting across on the periodic table. And then subtracting that from the 7 for nitrogen, that gives you this 2 that are here. So you could actually get the core electrons with simple subtraction. Do you see bromine? So here's bromine. I forgot my laser pointer, the blue one. If you want to get the valence electrons of that one, you're in the 4th level. If you start up where helium is and count down, you count down 4 rows. Maybe it's easier to count from the left because helium's weird. But start with hydrogen, you count down to 4, then you're in the row with bromine. So you're in the 4th level. But the potassium K and calcium, those are in the 4th level. But once you start across the transition metals, you're actually in the 3D orbitals. So if you want to know the valence for bromine, you have to skip the transition metals. And all of those on that side, you have to skip the transition metals. So bromine, if you count over to the left, you have to skip the transition metals. So bromine is 1, 2, 3, 4, 5. Skip way down here, 6, 7. 7 valence electrons for bromine. You see that? If you skip these, I'm saying skip this white fat part right here. If we're counting the valence electrons for any over here, we don't count these. You skip them and you go to the other side. No, that's not strictly true. That only works for bromine. Below bromine, you count them. Because below bromine, you've got the d orbitals. Is this right? No, it's above there. 3, 4, 5. That's the 3D. Yeah. It's the 4D. My brain just broke. 5. We'll have the 4D. 4. Yeah, below there. No, I'm right. You skip the transition metals. Bromine and everything in that row, that column, are all 7 valence electrons. Everything oxygen and then below oxygen, that whole column, those are all 6 valence electrons. You follow me? But if you're in doubt, draw the diagram. Draw the electron configuration diagram. It's always about this point my brain starts fading. So what should we do next? We still have an hour. Okay, let's just get through more of these problems. Condensed, write the condensed. I'll do the condensed for vanadium. Well, let's do bromine since I just mentioned it. Okay. Five. That's the 4s. 4s, 3d. P, S. Where did I say bromine? That's where we are. 1, 2, 3, 4. Okay. What's the number for bromine? Called the atomic number, but also that it means the number of protons.
35.
35. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. You said 35? 27, 28, 29, 30, 31, 32, 33, 34, 35. Four is the highest number occupied. You've got 1, 2, 3, 4, 5, 6, 7. 7 valence electrons, but that's what I just said before. You count from left to right, but you skip the transition metals. So now I want to write this. 1s2, 2s2, 2p6, 2p3s2, 3s2, 3p6, 4s2, 3d10, this is a D, 3d10, and then 4p, 4, 5. So there's the electron configuration. This would work. This actually shows the electron configuration. I think that's what the book is asking for here. And then the condensed would be, where are we? Argon. The condensed version is you would replace all of this with argon. So helium, neon, argon, and then you would fill the rest of this in. So I showed you this just to show you an easy way to get it all in front of you so you're looking right at it. And then it doesn't matter what way you're going to represent the electron configuration. You could even do these boxes. But that's my quick and dirty way to show you how to just get it right in front of your face so you can look at it. And then writing down an electron configuration should not be too hard. You guys with me? I know it's all kind of abstract. When we get to the front part of this chapter, it feels even more abstract. So if I wanted to ask, what else do I have there? 7, 7. Oh, let's go look at these. What did I skip here? Okay, y'all are okay with that. 7, 2. That's tedious, but I think y'all can do that. 7, 4. Valence electrons, I think y'all can do that. That's her duplicate. 7, 6, 7, 7. I think y'all can do those. 7, 7, and 7, 8. All right, so let me go to this other section. We also covered the quantum numbers, the 4 quantum numbers. 655. All right, let me write these down. So, it's 5. And let's double check these and make sure I even want you messing with them. So these are related to the ML, M sub L, MS. Okay. So there was and then there was L has these possibilities. N minus 1 down to 0, and it's plus minus. Just my shorting. So those two equations. I don't want to leave that there too. Zero, 1, 2, 3. Okay, so what did this ask? What number? 55. For n equals 4, what are the possibilities of L? So it's this. L can equal 4 minus 1 so L will equal 4 minus 1 is 3, down to 0, 2, 1, 0, and then the negatives, negative 1, negative 2, negative 3. For n equals 4, what are the possible values of L? For L equals 2, this is B, for L equals 2, what are the possible values of ML? L. Possible values of L. That's the possible values of L. Not plus minus. I better do this again because I've already messed up. I suppose we need to take a long break about this point where my brain starts to melt. I'm just stubborn. I don't want to get through it all. So this was 1, 3, 1, 3, 5. There is one more 1 there, but I wanted to relabel this 0, 0, 0, 0, 0. L number, so this is n equals 1, this is n equals 2, this is L equals 0, and this is L equals 1. But if you get to n equals 4, your possible values are, what the L values are these. So when you're at 4, you can have 1, 2, 3. Should have 4. Zero to n. 0 to n minus 1. Okay, 0 to n minus 1. So n minus 1 is here, so it's just 0. N minus 1 from, so 2 minus 1 is 1, so 1 to 0. 1 down to 0. 1 down to 0. Because it's 2 minus 1 down to 0. N minus 1 to 0. Here n equals 3. 3 minus 1 equals 2, so 2 down to 0. 2, 1, and 0. 2, 1, and 0. So if you're at the n equals 4 level, 1, 3, 5, 7. And this is L equals 0, L equals 1, L equals 2, L equals 3. So therefore, 4 minus 1 equals 3, so it's 3. 4 minus 1 is 3, 3 down to 0. 3, 2, 1, 0. Those are the possible values of L. So that's what this was asking, possible values of L, and that's the formula for it. N minus 1 down to 0 is the way I would put it. But again, if you'll just draw this and label it, it's all very obvious. These equations don't have to be that complicated. But the other one says, if you have an L value of 2, what are the possible values of N minus 1? What are the possible values of ML? So it's not giving us this. It's giving us this. L equals 2. Right? Yes, right here. L equals 2. Now, the values of ML, that's these. These are going to be n minus 1, just like before. Now I'm going to do the plus minus. So it's L to m sub L does the plus minus. And this is L. So if L is 2. So here is where L is 2. This is, it says L is 2, right? Yeah. It's not minus 1. Yes, that's right. So here L is 2. Here L is 2. Here L is 2. It's the d orbitals when there's 5 lines. Number of lines. And 2, yep, without the minus 1. So L down to 0. 2, 1, 0, and negative 1, negative 2. I just think the diagram's easier than the calculations. just in case your brain is working better later than mine is now. 0.2, that's 6566. Well, this doesn't give a table number or anything, but it's these. The principal quantum number can have these values. The second quantum number is these values. So if you want to mess around with those formulas, they're listed here. Magnetic number, negative L to L, I guess that's a better way to put it. I usually don't go that in-depth into these. So try those. Look at those problems one more time. And see if you can manage to not get confused like I did. 5.5, 5.7. This is way easier than those. 5.8, 5.9. Maybe I should hold off on 5.9. 6.0. Okay. But keep 6.2. 5.9 and 6.0, when we talk about exciting states, it'll keep you from getting confused. And you can ignore this, don't worry about the XYZ subscripts, you won't know what that is. But this is just saying if you're n equals 1 and L equals 0 and ML equals 0, are you in the 2p or the 1p or the 3s or whatever? Some of these are impossible, but if you draw that diagram the way I keep telling you to draw it, I think it'll be obvious, or you can use these formulas. But I want to get out of this chapter and go back to one thing from a previous chapter because it's what we're doing in lab today, titrations. So we get away from this abstract stuff. I think it might be worth me going over this again next time. Not all of it, but those tedious formulas that are breaking my brain. But I can do titrations. I'm going to go back to chapter 4. And I already know titrations. And we're going to do acid-base titrations. And I already know the problems to A and B, A and 2. So I'll outline how this works, but I think this is all kind of familiar to you guys. Okay. So this question goes blah, 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 but ultimately it's this. NaOH. Is that still going? Good. H2SO4. That's going to make 2H2O plus NaSO4. If I balance it, that's got to be a 2. There's a 2 there. There should be a 2 there. All right. 2 and A. Okay, that's balanced. This is an acid-base reaction. Okay. Here's the information you're given related to these two reactants. I'll say NaOH All right, so what are we given here? All of this is just blah, blah, blah. In one such analysis, 45.7 milliliters of 0.500 molar H2SO4. 45.7 milliliters of 0.500 molar 0.0. Three significant figures, three significant figures. So you've got your milliliters and you've got your concentration. And then it gives us for NaOH 20 milliliters of NaOH. NaOH. This is ultimately what you find out. But what they're doing is they're taking they take 20 milliliters of NaOH. So let me diagram this. I'll put these in a Word doc. Can I erase this? I want to keep the influence there. All right. So they went and got, like you might be doing today, NaOH, and what they got was so they know this. What they're trying to figure out is what is the concentration. They want to know the concentration of the NaOH. So what they do, you guys used a burette early on in the semester, the big long thing that we clipped into a, they put in here and what you do is you drip it little by little and you put an indicator in there. I haven't said much about pH, but if you have more base than acid, H plus, H minus, it's basic, and its pH will be, I'll say, its pH will be greater than 7. If it has more H plus than OH negative, that's a pH of less than 7. And we would call it acidic. All right, without saying any more about pH, there's a way to calculate it based on concentration. Two things I just haven't said yet. And basically what you're doing to find the concentration of the NaOH is you're neutralizing the NaOH. This is an acid-base neutralization reaction. And there's what you usually do is you put an indicator, like one little drop of a colored solution in here, one that changes color at exactly pH 7, so you know exactly when you go from basic to acidic, or acidic to basic. Like it's reddish when it's on the acidic side, and it's bluish when it's on the basic side. It's very red at very low pHs, and as you get closer to 7, it gets lighter and lighter and lighter red. And then right as you cross 7, it turns to very light blue, and then gets darker and darker blue. So you can literally see with your eyes the pH once you put one little drop of an indicator in. So they would have done that. And then they start little by little dripping H2SO4 in there. and they're watching the blue color change as they're putting more and more drops in there. Wait until the blue color goes away. It actually turns clear right in the middle and then starts to go pink and then darker and darker and darker red. They did that until they knew they were at pH 7 by the indicator. And once they were at pH 7 by that indicator, they stopped putting the H2SO4 in there. Then when it's completely neutralized, and then they read their burette, and it said 45.7 milliliters. So they knew the concentration up to 3 significant figures of this. They knew exactly how many milliliters they put in there. And they know exactly how many milliliters of the NaOH they have. So that's a titration. The way the calculation works is something that should look very familiar. Milliliters of H2SO4 that over 1, and then I'll go 1,000 milliliters to 1 liter. That, I tell you guys to think this moles per liter. So just turn the M into moles over liters. And then when you're going to use it in a calculation, so that's the way it's usually written. That's literally what it means, but if you're going to use it in math, go ahead and write it this way. That's what comes next here. 1 liter, H2SO4, 0.500 moles. H2SO4. All right, now we're at moles of H2SO4. Now we're going to use this, 1 mole of H2SO4 to 2 moles of NaOH. Make sure this is on camera. Okay, it's still there. All right. And now we're down to 20 milliliters of NaOH. Yes, 20 milliliters. It's got to be on the bottom. $20 milliliters of NaOH. So now I'm using that. Put 1 up here, and then moles of NaOH. So milliliters cancels, milliliters cancels, liters cancels, liters cancels, moles cancel, moles cancels. This will not cancel, and I just need to turn that into liters. I could have H2SO4 here and H2SO4 here. I just left the label off. This should be NaOH and NaOH, but so that's 1,000 milliliters to 1 liter. All right, that cancels out to milliliters H2SO4, milliliters H2SO4, liters of H2SO4, liters of H2SO4, moles of H2SO4, moles of H2SO4. Moles of NaOH will not cancel. Moles of NaOH. Milliliters of NaOH will cancel, and we'll be down to liters of NaOH, which is what we're trying to figure out, moles per liter. So the rest is the math. Can you tell I'm happy to get out of the quantum mechanics? Now I got a second wind here. 45.7 times 0.5 times 2 times 1,000 divided by 1,000 divided by 20. I think that's it. I got 2.285. .285 moles per liter NaOH. But it's got to be three significant figures, so it's really 2.29. I'll use the M. So by doing that titration and using a known concentration of an acid, they can find the concentration of that base by doing a titration. And that's literally what we're doing in lab. You could do it the other way around. You could have an acid that you don't know the concentration of and have a base that you do know the concentration of, and you can put the base in the burette instead of the acid. This is important, the balancing that showed up in here. So let's at least do that one. Still going. Let's do that one. It's either 8.1 or 8.2, 4.81 or 4.82. There's probably more examples here in the bulk of the chapter. So as far as titrations go, I can put this on test 3. You're only going to have this 4.81 for practice. I said A and B because C and D are precipitation reactions, but you could do this with a precipitation as well. But we're focusing on acid-base titrations. So do A and B there. I can do A and B here for 4.82. But for more practice with titration type calculations, your lab is going to have plenty of stuff there that you can answer, the pre-labs and stuff. That only helps you if I grade them and get them back to you, though, for the test. I'm still making Brendan do all the grading. So let's solve this one, 4.82 A and B. So you would have to balance these first. .82. So you've got HCl and you've got BaOH. So this provides Cl. This will provide Ba2 plus to the solution and 2 OHs. That's why I have to put a 2 here. So now I have that. And now these can make 2 H2Os. So be sure you balance any of these. And now we have the BaCl2, but that's not our focus. All right. And here we're told it takes 0.120 molar HCl. How many milliliters? Okay, we've got 50 milliliters of 0.101 BaOH. Milliliters. 50 milliliters, and then 0.120 milliliters of HCl, right? .120. All right. So we're going to start with this side where we have all the information. And it's going to be 50.0 milliliters. OH2, 1,000 milliliters